So indeed, I'll be talking about my work in computational pathology. So I think you did a pretty good job at summarizing my academic journey. Just want to say one more thing. I'm an engineer by training, so I'm not a pathologist and I'm not a mathematician. So please bear with me on these sides. So I did again like my PhD in Zurich, and now like my main focus, of course, computational pathology, computational oncology, and more we are moving towards like computational spatial omics data. So to start, because my understanding is not all of you are familiar with the field of computational pathology, I thought it would be good to kind of provide a high-level introduction and kind of like formalize a bit the problem. So here, when we talk about computational pathology, it's a bit of an abuse of language. It would be actually like computational histopathology, where the problem statement is usually the following. You're given with a digitized whole, like what they call a whole slide image, digitized tissue section, for instance, stained with H&E, or it could be any other stain. And your goal is to extract clinically relevant information or biologically relevant information directly from the tissue slide using an AI model. So this can translate in many different applications, ranging from oncology to like kidney transplant assessment projection, which we have worked with Harry. And again, there can be like many different applications. For instance, predicting clinical outcome, grade, stage, cancer subtype, being able to detect and segment different tissue regions directly from the image, right? So this is globally what we call computational pathology. And if you're a bit familiar with machine learning, what I'm describing here is pretty much a classification task. You have an input and you want to extract something out of this. Of course, there is a catch, and the catch is that like the size of these images is very large. And here you have an example where you can see, as you zoom in, the complexity and the hierarchical nature of tissue. So it may sound like a detail, but like this unique feature of whole slide images has basically been driving all the technological advancements of the field. So whatever we're going to develop and whatever we want to translate from computer vision and AI applied to imaging will not always translate to our field simply because of this size bottleneck, right? So if we take a historical perspective of the field, so we hear a lot about computational pathology for the past, say, 4 or 5 years. But actually, it's a field that started in the 60s with seminal work from Judith Prewitt from UPenn. And I think it's a very interesting paper that she wrote in 1965, where she says, oh, now we have high-speed data facilities which provide the ability to manipulate the hitherto unmanageable quantities of optical information. So spoiler alert, she was a bit enthusiastic with the assessment of the computational capabilities that we had back then. And despite this work very interesting and actually like laying down the foundations, at least conceptually, of everything we've been doing, it took about 50 more years to show that for the first time, an AI model could do and automate some task at least as well as experts and human experts. So one example among many, this paper published in Nature by the lab in 2022, which showed that an AI model was able to predict the origin of a cancer of unknown primary, which is a very complex problem in oncology. Again, one among many different examples, but that really illustrates that it really took 50 years of progress to go from one to the other. And this didn't happen without insane advances in digital diagnostics. And again, one important date is 2017, which was the approval of the first scanner for digitizing tissue slides. So again, something very recent. So the situation is people are excited about AI in pathology, but the reality is pathology to date remains very much non-digitized, and only 4% of global pathology is done on a computer screen. So again, it will likely take years, if not decades, to fully transfer to digitize and really implement and integrate these AI-driven methods. And of course, advances in AI and machine learning. And again, this paper from 2017, the Transformer paper that really changed everything in deep learning, AI, including computer vision, so the ability to look into images. And pretty much what we've been doing for the past 10 years is just like extracting more and more information all the time using the same backbone, the same transformer architecture, which has led to the vision transformer, which is really like the main architecture for extracting and doing anything with imaging. So one example of like applications which we can do is the ability to predict clinically actionable biomarkers directly from tissue slide. So this can have multiple advantages. For instance, on the clinical side, we could think that like if we have an H&E slide, we could directly predict some biomarkers, and this would be pretty interesting. For instance, to reduce turnaround time, which in some countries can be like several months or several weeks. Sorry. It's also a way to reduce costs because we can like screen patients that we think might be eligible to a treatment because they have this mutation. There's also a way to screen potentially for more molecular alterations because of course these tests are like molecular testing can be very expensive. And overall, on the clinical side, having the ability to extract directly molecular information from the slide can be a way for oncologists to make better informed calls. So that's on the clinical side. And then on the research side, this kind of applications can be very good to identify morphological biomarkers which align with some molecular alterations and some pathways. And overall, this can be interesting to identify new subgroups based on molecular features on some very cheap, very like widely deployed modality, which are reflective of the underlying molecular landscape of the tissue. So a lot of people are very excited about this direction, which has received like a lot of attention over the past, say, like 4 or 5 years with some very recent papers. For instance, this one published in Nature Communications. And overall, we can say that we have about 200 studies that show that it is possible to extract molecular biomarkers directly from the tissue morphology. So from the beginning, I just say, oh, we just build an AI model and we just train it to extract this, or this. But of course, and again, because of this size constraint that I was talking about in the beginning, it is very, very challenging to be able to extract the right information from these whole slide images. So the field has converged to what I call like this 2-stage pipeline, which people sometimes call like weakly supervised multiple instance learning. Again, it's a pretty barbaric name to describe a 2-step pipeline, which is not that hard actually, to transform this like huge image, which can be like several gigabytes, like 2-3 gigabytes in size, into, for instance, just the grade associated with the tumor found in the slide. And again, because the size of the image is so big, well, we just follow like a pretty intuitive approach. We just break it down into like small images, which we call tiles or patches. Maybe we're going to have like 10,000 of them per image. And we're going to have a model, so like just something that is good at compressing the information into what we call an embedding. And we're going to do this individually for each of the tiles that constitute the image. And we're going to obtain like a set of, say, like 10,000 of these embeddings. And then what we want to do is aggregate and ensemble all these embeddings into one slide embedding, which is like a very compressed, very information dense. And if we did a good job, an embedding which should encode all the clinically relevant information and all the biology found in the tissue that can finally be used for classification, again, for instance, for predicting the cancer subtype. So as you can imagine, training this, even if the pipeline is pretty easy, is no easy fit. And the reason is typically it requires a lot of data for doing this, and it is not always feasible. If you want to do Gleason grading of prostate biopsies, we have a lot of data. So it's kind of an easy situation. Biopsies are rather small images for pathology, again, small quote. So we can do it. But considering the complexity of all the problem statements that we have in oncology, we keep getting like more and more complex. It's pretty much impossible to develop from scratch a new solution. So then comes the idea of like, how can we build a system or a model such that we don't have to reinvent the wheel for each new application? And this is basically what the field and my research is about, is how do we make sure we don't keep redeveloping the same thing over and over? And this can be done again at both levels. The first one is to be able to encode these small images and the other one to be able to encode the compressed representation of these images. So if we start with the first stage, this patch encoding, again, this idea of not reinventing the wheel has motivated this work called UNI, which was published in Nature Medicine last year. And what we do here is we just extracted like a very, very large data set of over like 100,000 whole slide images from like very diverse sources, so like a very, very diverse data set. And we train a model, again, like this transformer that I was talking about before. So it's a vision transformer large model, which we train using a training recipe called DynoV2, but again, the name doesn't really matter, but it's just a way of pre-training this like huge model and being able to compress information in a complete task agnostic fashion. And if we did a good job, then these compressed representations and the embedding that we can extract from all this style that constitute the whole slide image should, in theory, be able to generalize to many, many, many different downstream tasks. But of course, we have to prove it, right? So back then, we designed what used to be the largest evaluation for pathology, where we had like 33 downstream tasks covering like multiple tissue types, multiple diseases, and so on and so forth, where we really showed that this model indeed was able to deliver better performance. So since UNI became a reference in the field and is now being used by thousands of users. So we have this ability to encode images into compressed representation. Now the question is, can we kind of inject additional properties into our pre-trained model that ideally would bring something else than just the ability to encode information? Encoding is great, but we encode into an embedding space. And this embedding space is by definition, by design, completely non-interpretable. It's just a bunch of scalar numbers, which are not of a lot of value if we actually want to interface with the model. And the way humans interface is with language. So for this purpose, we designed Conch, also published last year in Nature Medicine, where we gathered like a data set of over 1 million pairs for which we have an image and its corresponding text description, right? So you have an overview here, again, like very, very, very broad and generic data set with a lot of variability, multiple stains, a lot of H&E, of course, but not only, also a lot of IHC stains, a lot of special stains. And we basically train a model to be able to align these two modalities such that we kind of induce the ability to interface with our vision encoder, which was designed earlier, right? And here again, if we say that we have a foundation model which can kind of interact with the way humans typically do, so like with language, we also need to prove it. And again, we designed like this big benchmark where we show that Conch was able to deliver better performance. So we designed all these models. The world is beautiful. The performance is great. But then comes the question, are these models behaving the same way for all the different patient demographics and for all people? And in this study, which we published last year, we really decided to study this and understand that there is like a gap in performance between patients of different ethnicities. So we took a bunch of foundation models, including UNI, and we tried predicting like multiple tasks, including like lung cancer subtyping, breast cancer subtyping, and mutation prediction in brain cancer. And we stratified the performance by ethnicity. And what we found is that like significant variations between different populations. So it's very, very hard to know exactly why this is the case, because pathology in the way it is taught in medical school is not driven or biased by the patient ethnicity. But still here, it's seen that the AI model is learning some biases. So overall, the conclusion of this paper was like, well, before putting a solution or a product in the market, well, we really need to make sure that we understand exactly what is happening, and doing this kind of stratification based on multiple variables like ethnicity, maybe income, and so on and so forth is also important before putting these models out there. And here you have like an overview of like this like patch level models, which are again able to encode a small pathology image into an embedding. And now let's go back to our two-stage classification pipeline. So as I was saying in the beginning, we did a lot of work on the first step of the pipeline, ability to encode images into embeddings. But then there is like the second stage. And if we want to classify our whole slide image, we still need to learn the second stage of the model, the slide encoding, from scratch. And this requires a lot of annotated data. Sometimes you have it, but in many, many cases, you do not. So that's the first big limitation. The second thing is that the slide embeddings, which are resulting from whatever downstream classification task you do, will be by definition biased towards this task. You don't have the ability to have task agnostic slide embedding without doing something with this second stage. So the question now is, what if we make stage 2 a general purpose model? Well, this would enable at least 3 properties. The first one is case stratification, where we could automatically encode your whole slide image into an embedding space and then do different things with it. We can stratify different populations automatically off the shelf, something you get. The second thing is case retrieval, where again, you can take the slide embedding and just if you have a bank of different slides, you could try pulling the most similar cases just based on the tissue morphology. Second property. And third property, which is maybe the most interesting one, is the ability to learn with very few annotations, called few-shot learning. Because now our pre-trained model is already capable of encoding our entire whole slide image, our huge object, into something very compressed and very information-rich. So the only step we have to do is maybe training like a logistic regression model to transform this embedding space into whatever classification we have, right? And while the motivation or the intuition, I think, is pretty clear, there's the question, how do we do this? And our idea was like, what if we could use expression data, which, again, as I was saying in the beginning, is partially reflected into the tissue morphology as a way to guide the representation. So our idea is that expression data can offer a holistic view of the transcriptome, some of which is reflected into the tissue morphology. And most of these interactions between genotype, phenotype are completely unknown to humans. We just know they exist. But here again, we can design a model which just implicitly learns these interactions. And if we do this, we have a model which is completely free of human biases and human concepts, such as grading. It's just purely data-driven. So this has motivated a series of studies, including the latest one called Threads, which is currently under review in Nature Cancer, where the idea is we take a very large data set for which we have both the tissue slide and the corresponding molecular profile. It can be NGS, it can be whole transcriptome RNA sequencing, anything. But the idea is that we have those two different views of the same state of the disease, and we find a way to align these two modalities into an embedding space. And again, if we did a good job, well, the resulting embedding space should be able to naturally highlight the underlying molecular profile of the tissue, which is exactly what happened and what we did here. So what you can see here is a TSNE representation, where you can see that naturally, without any form of explicit supervision, just guiding with molecular data is able to identify multiple diseases and multiple sites and organs. Again, completely data-driven. And now, it's following the same story. You claim you have the best foundation model in the world, and comes the question, prove it. So for this, we designed what is now today the largest evaluation in oncologic pathology. It's called PathoBench. It's around 54 tasks that cover a very wide spectrum, predicting mutation, doing some cancer subtyping, some cancer grading, predicting directly treatment response, predicting survival, predicting IHC directly from the H&E. So there's really a galaxy of application, and we really try to be as comprehensive as possible. And when testing it against existing methods for doing this, again, we show that we have much better performance. So doing benchmarks is good, but it's even better if the benchmark becomes public so that people can actually reproduce and build upon that. And that was the idea behind the PathoBench. So out of the 54 tasks which we have, 42 are actually from public data, which we have curated, and we provided all the labels, we provided all the splits to really make sure the community can start working with this. So 42 tasks is good, but we can do better, and this is what we're currently working on. So we now have about like 130 different tasks. So we almost multiplied by 3 the size of PathoBench. And hopefully this will be released in the next, say, 2 months. And again, will bring a level of magnitude and really confidence in the quality of the model, which is again, much better. So benchmarks, again, are great. Developing models, it's good, but it's also good if you have a way to kind of like easily extract all these embeddings, the patch embeddings, the slide embeddings. And this is why we built a Python library called Trident, which is also publicly available, which is basically aggregating all the existing foundation models, plus a bunch of other tools like the ability to patch the slide, ability to segment the slide, all those things. And it should be very, very easy for users that maybe are not very familiar with the field to really onboard and start working with this. Okay, so now back to our first stage. So we were basically saying in threads, well, using expression is a very good way to guide the representation. So what if at the patch level, we kind of follow the same idea and we use spatial transcriptomics, which again should partially, like the morphology should partially reflect the transcriptomic profile at a very fine-grained resolution. The problem is like spatial transcriptomics is not a clinical modality, and we cannot like directly use clinical data and go to the hospital. No, like spatial transcriptomics is still used in research only. So it's very, very hard to get access to a lot of data. So what we decided to do is, okay, let's try to unify as many ST data that we can find and try to make a data set out of this so that the community can actually start scaling any form of ST experiment. But we want to do it the right way, and we want to make sure that like for each ST profile, there is like a number of things that come with it, including the corresponding aligned H&E whole slide image. And this is what we did. So we extracted about 1,200 ST samples with corresponding H&E whole slide image from 151 different cohorts from 2 species, including healthy, cancerous, and diseased tissue. And this overall corresponds to a bit more than 2 million spots, ST pairs, and a total of like 76 million cells that were detected. So this is all public. So it's all hosted on Hugging Face. So again, it should be pretty easy to download. And one small note here is why only 1,200 ST? Because actually, if you look at this paper, there's been around like maybe more than 2,000 studies doing ST. And the problem is a lot of people are not publishing the corresponding whole slide image at high resolution. So we only have the ST profile, but if we really want to understand the correspondence and the matching between morphology and transcriptomic, we need both. So that's the main reason for why we only have 1,200 samples. So people are using the HEST 1K data as its name. We've had more than 200,000 people downloading it. We have about 1,000 active users, including people from Australia. So like this map is not up to date. Maybe there are like more dots now in Australia. But again, like people seem to like it and start building things with it. So having data is good, but having a library to help working with the data is even better. Because like whole slide images are challenging to work with. You usually need to use OpenSlide. You got to use something called like A-data objects from ScanPy to use ST. It's a little dry for newcomers. So we need to make them more accessible for maximum impact. And that was exactly the idea of the HEST library, where we have a way to query an interface, HEST1K, loading with a bunch of legacy readers and so on and so forth. We also have the way to align multiple things like the image and all the spots. We can do nuclear segmentation. We can visualize some batch effects, correct them, and so on and so forth. And again, HEST library is public. So feel free to check it if you're interested in this kind of work. From the HEST data set, we were able to derive a benchmark where we really wanted to understand what are the current predictive capabilities of the foundation models and which of the foundation models are actually better. Because let's say over the past 18 months, over 20 people have claimed that they have the best foundation model for pathology. And the question is we just have no idea which one is best. So we designed this task at patch level where the goal is to predict highly variable genes directly from tissue morphology. And what we highlighted for the first time is that there is a scaling law between the number of parameters that have been trained in our foundation model and the downstream performance. So it seems that there is an interest in having bigger models, bigger foundation models, but this gain only grows logarithmic. So again, it depends on your hardware capabilities. There is a bit of a trade-off here, right? And we can see that there is a lot of variability across models, even if you use the same training recipe and the same model size. So not all models are created equal. So here again, trends matter more than the absolute performance. It's just a way to benchmark all these different foundation models, which again, most of them have been published in high impact journals in 2024. So this scaling law that we observed in model scaling, well, to some extent translate into data scaling. So yes, increasing the number of training patches seem to be helping, but there is a number of confounding factors. Maybe the number of slides matter more than the number of individual patches. Maybe the diversity of the data is more important. Maybe it's also interesting to have more non-biological diversity, for instance, data that come from multiple scanners and so on and so forth. But again, we were able to highlight this kind of trends. So there's still a number of limitations in HEST benchmark. It's still small tissue regions. So maybe scaling would be more interesting. And again, the batch effects, which are inherent to any ST, are still poorly understood when we scale to about 1,200 samples. This scale hasn't been really studied in detail, right? Of course, we can apply the same recipes as what we were doing before. We could use the corresponding spot with the tissue morphology to just align both of these modalities and hopefully show that whatever scaling law that we're able to show can be boosted if we do some transcriptomic alignment. In other words, we kind of push the model to be able to encode the underlying transcriptomic profile. So it's still very much ongoing work, so stay tuned. We're probably going to preprint an article in the next 2 months about this, but it seems that this kind of approaches is relevant. So if we try to understand where do we stand as a field, this is my current analysis. Is that the AI researchers today are developing these very, very large models, over 1 billion parameters. There is very large disease diversity, many modalities. Our benchmarks are much better. So this is all good. I think medical doctors are usually open to AI integration, which is also good. Experimentalists or biologists are usually interested into AI tools, especially for identifying and quantifying biomarkers. But the problem is that the advancements or the pace at which AI moves forward is likely too fast for biologist experimentalists to really keep up. So there's little translation going there. And I think the same holds. There's little translation from AI models direct to medical doctors, simply because most AI researchers are not interacting that much with oncologists and pathologists. So what are we doing wrong? Or at least what are the current limitations of these foundation models? I think one of them is that these models are encoder-only models. Or in other words, they are not a product. What you get is not actionable enough. They cannot provide off-the-shelf information. And ideally, we would like them to provide quantitative information from the slide without any form of fine-tuning, without even barely any knowledge of computer science. I think a third problem is that we are too focused on H&E staining, where actually pathology both the clinical side and the research side is more and more using immunohistochemistry and spatial stains. And finally, the last problem is our current foundation models have very limited capabilities in interacting with the model. We are still at the beginning of this, especially in answering one question is how can we optimally integrate prior knowledge in whatever we develop such that we can really combine the understanding, intuition of researchers and clinicians along with the power of AI models. So these are like all questions, all things that we need to work on. And overall, this is calling for the development of a new generation of foundation models, which likely will be what I call like AI assistants for pathology and for oncology, where we really want to design this form of like copilots that will be able to address at the same time tasks which are quantitative, like quantify the amount of necrosis in the slide, count the number of TILs, and so on and so forth, but also having a copilot which can address qualitative tasks. So answer like, oh, what do you think is your diagnosis for this, and so on and so forth. And this should be able to be done like across multiple modalities. And like this is a new field called agentic AI, which is again like a fancy name just to describe this kind of models where we are really able to develop one interface, which is where the oncologist, pathologist, or researcher is going to interact with the model with language. And what we're going to do is have a toolbox of different foundation models which are capable of doing different things, like quantifying necrosis, quantifying TILs, describing the immune landscape, captioning some different regions, and so on and so forth. And we'll do like multiple calls to all these tools in our toolbox to overall answer the query made by the researcher. This is also a great way to integrate prior knowledge, because the researcher, the oncologist could say, I think this might be this. What do you think? Oh, actually, let's use another tool to confirm whatever intuition was made. So we are very much developing this kind of tools, and we expect a lot of advancements in this direction in 2025, 2026. So again, this is really the future. We need to be able to build AI models that can really assist research in oncology and pathology. And for this, we need support for multiple modalities. And the goal is really to bring the right tools, the right set of tools to the right people, to the people that have the right problem statements, right? We also need to be able to do information retrieval. Maybe we could imagine connecting these agentic systems to like some kind of bibliography or Mendeley, so that you can directly query information from the list of PDF that you have. So you know that whatever information is being pulled doesn't come from Wikipedia, but comes actually from a set of published paper that you trust, that you have read before, right? And I think, or like likely in 2025, we're going to have like more and more of these models which really bring off the shelf capabilities for cell segmentation, tissue segmentation, and phenotyping. And finally, I think we need to also like rethink the way we evaluate models. So we worked a lot on retrospective benchmarking, but we need to go more and more into prospective benchmark and what we call zero-shot evaluation. So voila, that's pretty much a tour of computational pathology. And before concluding, I'd like to thank all my colleagues and coworkers at the Mahmoud Lab. I'd like to thank you for your attention. I'll be happy to answer your questions. Thank you.